Hello, my friend. Several days I haven't updated my videos. So today we will focus on the question related to the NMOS amplifier. First of all, hopefully you are safe in anywhere in this world because currently there are some wars happening in this planet. Yeah, I don't know which side is correct, is right. But be safe, my friend. That's the most important thing. Okay. The MOS transistor is a fundamental element in today's IC industry. And the basic structure for the NMOS is like this. Okay, this is the substrate, which is mostly doped, P-type doped, which means we just doping the fifth group of elements into the silicon. We can get the P-type, substrate. And here is a N-type area, which is doped by the third group of elements, and we call it a source. And here is D, which is called a drain. This area is also doped by the third group of elements. Above this area, there's a silicon dioxide layer, very thin, and it is dielectric. Just above the silicon dioxide, we call it gate, and this is a polysilicon. Okay, so if we apply a positive voltage between the gate and the source, the VGS, there will be a channel formed by the electrons just under the silicon dioxide. So if the VGS is large enough, which can be greater than the threshold voltage, the electron channel under the silicon dioxide is long enough, which can connect the source and the drain. So we have a vertical electrical field, and currently there's still no current between source and the drain because there's no horizontal electrical field. So we can apply another voltage between source and drain, which is VDS. So presently, we can make there generate a current which is flowing from source to drain. And if the VDS is large enough, there will be a phenomenon happen in the channel, which is called pinch off. So that's the basic idea. So the current between source and the drain, we call it ID. Okay, we call it as ID. And the feature between ID and the VDS is look at like this. Okay, there will be three areas. So this one is the first area, this one is the second area, and this one is the third area. The first area is called cut-off region, which means VGS is smaller than VT. So basically, the NMOS is working as a switch for the circuit. This one means the switch is not open, it's all off. And for the second region, it's called a linear region or triode region, which means the ID current will be increasing with the increase of VDS. All right, at this area, it is VGS bigger than VT, and the VGS subtract VT is bigger than VDS. The third region named saturation region, which means VGS is bigger than VT, and the VGS subtract VT smaller than VDS. So the third region is our desired region. All right. Okay, that's some background knowledge. So we will focus on this question itself. In this question, the threshold voltage is 2 volts, and the Kn is 6 milliampere per square volts, and the Lambda is this number. As we know in our textbook, in the saturation region, the ID has this relationship with VGS, all right? Like this. So this equation is valid with lambda is 0. So remember it. All right. This is the structure of our circuit, which is NMOS amplifier. And then let's look at the first question. It is asking which configuration is this structure? All right. We can see the input signal is applied in the source, okay, in the source, because this is a structure for NMOS. We can see this arrow. The part with the arrow is the source. This one is a drain, and this one is gate. All right. Okay. So the input signal is input through the source, and the output signal is from the drain. Okay. This is drain. This is gate. This is source. Obviously, it is common because the input is from source. Okay. And the output is from drain. So the structure or configuration for this amplifier is common gate. So this is a custom for the amplifier, even for the BGT, which is bipolar transistor. Yeah, you know it. In bipolar transistor, this is a base, this is a collector, this is emitter. Okay, if we apply the input into the base and output from the collector, it's common emitter. Yeah. All right. So the answer or solution for the first question is straightforward. Next, let's look at the second question. It is asking us to calculate the value for R, okay, for R. And with the condition that the ID is 3 milliampere and the lambda is 0, all right? Okay. So because the lambda is 0, so all the drain current ID will flow through the resistor of R. Okay. And so apparently we know the current through the resistor R. So we want to get the value of R. We just need to know the voltage that across the resistor R. So that's the basically idea. All right. So let's just do it to solve the voltage that across the resistor R. By definition, we can know the ID equals KD VGS subtract VT square. Okay, we know the value for the ID, it is 3. Be careful here, the 3 milliampere, all right? But for the value of Kn, it is 6 milliampere. So milli, both sides is milli. So I don't write the times 10⁻³ power, because at each side of this equation there is a milli, so they will be cancelled for each other. So I just write 3 here. Yeah, be careful this thing. So half of the 6, all right? VGS subtract VT, which is 2 volts. Okay. By this equation, there's one single equation and one unknown variable. So we can easily solve the value of VGS as 3 volts. Okay, 3 volts. So VGS is 3 volts. VGS equal VG potential at the gate, subtract the potential at the source, which is 3. Sorry. Because the gate is conducted directly to the ground, so VG is 0. It should be like this, all right? So we can solve the potential for source is -3 volts. So next is quite straightforward. Why? Because the VS is here, and which is at the top side of the resistor, okay? And the other side, the potential is -6. So we can directly get the equation like this. So this is our drain current ID, which is 3 milliampere, right? So it's 3 milliampere, which equals the voltage across the resistor R. So it is -3 Vs subtract -6 and divided by R. We can conduct it like this. Vs is -3 subtract -6 divided by R. All right? So it's easy to get the value of R as 1 kilo ohm. Okay, 1 kilo ohm. All right. So presently we get the value of Vs, which is -3 volts, the value of R, which is 1 kilo ohm, and the value of potential at drain is calculated by this, which is VDD subtract ID times R, which is 6 subtract 1 kilo ohm times 3 milliampere. Okay, kilo will be cancelled by the milli. So it's 6 subtract 3, which is 3 volts. All right. So the value of VDS will be straightforward, which is VD subtract VS, which is 3 subtract -3, which is 6 volts. So we get the value of R, we get the value of OVGS, and we get the value of VDS. All right. So we can finish the question B. Next, let's focus on the question C. It is asking us to calculate the amplifier or the gain, voltage gain of this amplifier. Be careful, it is small signal. Here we must get known how to understand the small signal. Or consequently, whereas the large signal. So large signal mostly means the DC biased circuit. Okay, DC biased circuit. We use the DC biased circuit, the large signal, to make the amplifier is working. Okay, is working in the saturation region. Okay, saturation region, and the signal, the small signal means the AC signal. For example, this is ID, this is T, this is large signal, the DC ID. The small signal is like this, okay? Yeah, it will be superpositioned with the DC signal. All right, so we call it a small signal. Why we call it small? Because the amplitude of the AC signal should be much less in the DC amplitude. So which we will avoid if you have the amplitude of the AC signal is too large. It will make the signal, the working area from the saturation to the triode or to the cutoff. Yeah, but that's another story. So just you just need to understand the basic background. All right. So The third question is asking us to calculate the voltage gain of A and the input resistance R in and the output resistance R out. In this situation, the lambda is no longer 0, it's 0.02 divided by volts, okay? And the question itself is also mentioned we should use the T model for MOS effect. Yeah, because basically in the small signal equivalent circuit, we just two types. One is a pi model, the other is T model. Okay. So first of all, we will draw the T model equivalent circuit. It should be like this. Okay. This is our resistor at the drain. This is our ID. This is our output voltage. And the next, it is a embedded resistor, which is a transconductance reciprocal. Okay. Next is our signal. This is our input signal, which is a small signal. Okay. And here is the same resistor at the source, and it will be grounded just under this resistor. And here is our gate G. Okay, this is our gate G. Here is gate D. Here is gate source. All right, because you might be confused because we mentioned this many times in the textbook, there should be no current in the gate for MOS transistors because there is a silicon dioxide just under the gate, which means, yeah, there will be no current in the gate. But why here there's a wire? Because you can see here, yeah, the VGS times this divided by the transconductance, the result is ID. So the current in the drain and in the source, they are the same, which means in this branch, there's no current. There's no current. So this equivalent circuit is our T model equivalent circuit. Yeah, be aware of this thing. All right. Next, we will calculate the GM, which is the transconductance, which can be read like this. Sorry. So it is ID partially differentiate by VGS. Okay, because we know the expression for ID is like this square. So it's very easy by basic calculus knowledge, we get the GM. Okay, this square it will be cancelled by this 0.5, and we can get it like this. Okay, so it will be like this. Okay, we just put the value into the voltage into the equation. We can get like this, which is 6 times 3 subtract 2, which is 6 milliampere divided by volt. Okay, this is the value of GM. All right, so it's very simple to get the value for input resistance, which is just a reciprocal of GM, which will be this thing, and the answer is 166.67 ohm. All right, yeah, because this is the expression for our Rin. Why? because R in equals V in divided by R in. Okay? Okay? It's like this. So V in is what? It's our VGS. Okay? The I in is what? It's our signal. Okay? Okay? Signal. So this result is the reciprocal of transconductance. Okay? So we just calculated the value for the input resistance. Now we will try to calculate the output resistance. First of all, we will calculate the RO. RO is the embedded output resistance. So if the lambda is 0 as the ideal or perfect MOS transistor, the R0 should be infinite. However, for this question, the lambda is not 0, so we will get the finite value for the R0, which is lambda ID reciprocal, which is like this, 3 milliampere, which is 16.67 kilo ohm. All right, kilo ohm. So if we have the value of embedded output resistor and this output resistor as SR, the relationship between them is parallel. Okay, so the total or practical output resistor is R0 parallel R, which is 16.67 kilo ohm parallel 1K kilo ohm. So the answer should be 943.42 ohm. Okay. All right. So presently we have the input and output resistance, so we can get the output voltage as ID times R0, the total output resistance. Okay, the ID is what? ID is GM times V in, V input. And the R0 is just, we calculated this value as R0. Now it's quite straightforward because the gain for voltage is V out divided by V in, okay? Which is, we just put the V in back to here. It's GM times R0 equals 6 times 10 power to minus 3 times 943.2. So the final answer will be 5.66. That's the final answer. All right. Okay, I think we just solved the whole problem for this question. Hopefully, we can get some better or deeper understanding for how to understand the NMOS amplifier and the T model equivalent circuit. Thank you very much. Be safe, be happy, and my friends. Thank you. Bye-bye.